like a cartoon, just to show off, to show how this network would be. But in reality, if we look into this network, we have the solvent, we have unused water, or some kind of liquid, and the main product here. So if we do the aerogel, now look into the size of this product, okay, and look at the liquid what we have here. So we can clearly, we can clearly understand the fact that when we do this kind of process, there is a shrinkage in size, okay. But this shrinkage is not too much, but it's approximately less than 15% of the actual volume or the actual weight of the product or the wet gel. But on the other hand, if we are drying it completely to form the zero gel, which means I'm removing all my solvent, I'm removing all my unused water and all. So what happens when everything is removed from this network? Look at this size, okay, which is completely now shrink up to more than 90% of the original weight of the product or the gel. Okay, so this is just to make you understand like how beautifully we can, turn around the concept of solar technology based on what we finally want for our application area. Okay, let's go further. Now, we have understood one basic reaction, which is the hydrolysis and the condensation reaction, which converts the salt into the gel, wet gel form. Now, what happens sometimes we are in a hurry. So what we do is that we prefer to have some kind of catalyst for our reaction so that we can have an early product. Okay. So in this area, in this technology, we have the option of using either an acid or the base. And the beauty of using the acid and the base here is to actually, redefine the final surface morphology of the gel. Okay, so if I use in the reaction some kind of acid, for example, sulfuric acid, the most chosen one here. So the integrated network will be like, like an entangled, like a fibrous, like a branched thing kind of structure. But on the other hand, if I happen to choose a base for the reaction, for example, sodium hydroxide or potassium hydroxide, then instead of having this kind of structure, I may end up having the gel in this small, beautiful, flowery kind of structures. Okay. So again, we have the option here just to fine tune the reaction in a way that what we want finally for our application area. So the mechanism behind it is that some of us are organic chemistry here from the discipline by discipline. So if we see we have a nucleophile here, it attacks the positively charged center, and then it removes this alkoxy group, which is a leaving group. So basically, to understand that fundamentally, to go into that level of undergraduate reaction mechanism, it has to be a substitution by a nucleophile. So I would preferably call it nucleophilic substitution reaction. But at this point of time, I might not be able to define it as an SN1 or SN2 reaction, because we need to do those fundamental rate of reaction kind of experiments to understand if it is an SN1 or SN2 reaction. But on a bigger perspective, it's a nucleophilic substitution reaction going on for soil gel technology. Okay, so let's go into further deeper fact. When we do acidic hydrolysis, what happens? And when we have the basic hydrolysis conditions, what happens? So we have this monomeric, structure, the structure in the sol form, or the structures in the colloidal form, and then at the gel point, these things enlarges. Those monomer enlarges, into the oligomeric form. And then at the gel point, we see this are moving close to each other, just not because they want to, but because of all those fundamentals of chemistry, the electrostatic interactions and the charge transfer and so on. And then when we further proceed with the process of forming zero gel, then we can see a huge network here, or the more aggregated form of the polymer. Then whereas when we talk about the basic hydrolysis conditions here, when we add a base to the same sole, what happens? It starts forming a small, oligomeric form right at the beginning. And at the gel point, those small oligomeric network, they come closer, they enlarges, and when it becomes a zero gel, we could easily see it's a huge network here. But those networks are small little networks when we use the base. So again, just to make you understand like how we can uh, do the nano engineering right at the beginning to define, or different kinds of shapes and sizes of the network, what we like to have. So I'll just quickly draw your attention to these photographs here to make you understand that it's to our naked eye we can't see anything, but when we take those aerogels and zero gels and all the networks under a huge microscope, we call it transmission electron microscope, to see how what are the differences. So sorry, the picture is however not clear, but just to make you understand that if we assume that this is a zero gel, that under that huge microscope where we can actually see the product in our in our original or the pristine shape, then we could see that how the network would look like. Or if we have zero gel, the wet gel base catalysis, then how the network would look like. Again, as a colloidal form, how the random packing would look like, or if it is a dry gel, we can see a more compact structure. Now, we can also relate our understanding with respect to the nanoscale here, that how the scale is changing from the acid catalysis to the base catalysis, and how we can understand the different shapes and sizes of the gel forms by these methods. All right. So now there are further insights which I would like to share, is that when we do this kind of technology uh, and we have to design a particular material, we can nano engineer those materials with respect to the pH, with respect to catalyst, with respect to time, with respect to the solvent, with respect to the agitation and temperature. So, just how we have to understand this concept. So, what I would say is that let us first go back what we just now understood about the acid and the base. So, what acid and base will do? It will change the pH. What acid and base is? It's a catalyst. Okay. So, those catalysts are changing the pH of the reaction so that I can get a certain shape and size and porosity and yield of my final product. Similarly, if I talk about the time, if I stop the reaction very early, then I will have a completely different shape and size of my product. And if I delay the reaction for, let us say, I proceed with 4 to 5 hours, then it's almost a bit more different from what I have been doing for an early stage reaction. Similarly, the solvent. So I can have a protic solvent, I can have protic solvent, I can have non-polar solvent. So it's up to me how I would choose to proceed with the reaction. Okay. Similarly, agitation, what is the speed of the reaction? Okay. Well, agitation is nothing but the speed of the reaction, as well as it goes with the temperature also. If it is, I'm using the room temperature, or I'm using some high temperature for my reaction. So these are few factors that will have an impact on the overall production of the product. Okay, so further going deeper into the some of the application areas of this technology is that it is employable in constructions, it is employable in catalysis, in the textile industry, in agriculture industry, biotechnology, nutraceutical medicine, and so on. So I'll be just showcasing you some of the applications where you can understand the concept, how this soldier technology helps these industries out. Okay, now before I proceed with those application areas, I would also like to draw your attention to the soldier concept, which is non-hydrolytic. Now, what is non-hydrolytic is nothing, simply when I don't want to use water in my reaction. Okay, so there are possibilities that I don't have to use water, and I can choose to have certain medium or the solvent, and I can choose to have alkoxide, and I call it that kind of soil gel technology as a non-hydrolytic soil gel process. And again, different application areas of this as well, more or less similar to what is like what we can what we have understood for hydrolytic soil gel technology. All right. So, yeah, this is the application area, one of the application areas that's using soil gel technology. We are able to design the quantum dots, okay, for the electrical and the optical applications. So, what is the possibility if we choose different types of soil gel reactions? We are able to design different types of quantum dots, and you can see in this particular picture that if we restrict the reaction conditions of soil technology, we will arrive at different sizes here, which I'm mentioning here. And then if we have different sizes of the quantum dots, so what is a quantum dot, first of all? So to all those students, the quantum dot is a nanoparticle, is a particle which is in nano size, okay, but it is a semiconductor, okay. It's a semiconductor which is in nano size, as simple as that. So if I have that semiconductor or the quantum dot in this size using soldier technology, then that quantum dot will have completely different interatomic interactions and quantum mechanical properties. And it is, I mean, for your convenience, I'm just showing as an example that if I, if I put light on these quantum dots, you can see the different colors are, emitted from these different samples of quantum dot. So that's the beauty of soil gel technology. Okay, let's proceed in the cosmetic industry, how the soil gel technology plays a huge role. So in a cosmetic industry, we have different types of options, right? For example, we have sunblocks, we have mascara, we have perfumes, anti-acne creams, we have hair restoration treatments, and so on. So in all these different types of cosmetics which are available in the market, so soil gel technology are producing one of the component which becomes the formulation of these, big products. So it's a small little component, the gel component, which is very effective to participate in sunblocking, or which is participating in, that mascara. I mean, if you cry, mascara mustn't fall. So that kind of, the concept, the technology, and the anti-aging cream, the hydrogel face mask. So I'm not sure in India, but here in some of the international markets, I've actually seen these products which are black, and they say it's like, hydrogel based on some carbon nanoparticles and so on. So these are available in the market. Okay, the technology is there in the market. It's only that how we relate our, understanding how we relate our research into the commercial products. Okay, let's proceed to the work which I have done in this particular field. So this is one of the field or the area where I used soldier technology, which was developing the silicon carbide nanofiber or ceramic nanofibers. How did I do it? So how did I export this technology to reach the nanocomposite in the serum? Sorry, I'm missing the term here. The silicon carbide nanofibers. So I use this. Let me make you understand about the technology. So this process, the soldier process, just relate that concept which I was telling just previously a couple of slides back, that I was using the monomer, I was using the solvent, I was using the water, and then there is a particle growth which we call the gel. And then once the gel is formed, then we proceed to incorporate that gel into some kind of material which can give me carbon. So I have a silica and I have a carbon. The silica I'm deriving using soldier technology, and carbon I'm deriving with some kind of carbon source. So I used a source which is like this waste material, the lignin from pulp and paper mill industrial wastewater. I extracted lignin and I did mix the two, the soldier derived silica with this carbon, and then I used the normal production reactions, the reaction conditions of very high temperature of 1400 degrees Celsius in the atmosphere, the argon atmosphere, and then I could receive the silicon carbide here. So based on the same fundamentals of developing silicon carbide, I chose another material, which were the wood pellets converted into wood chars, and then I did the carbothermal reduction, the same kind of reaction conditions, and I happened to use this. I happened to achieve this silicon carbide. Now, to those students or to those budding scientists, I have a request. When we do research, please do not always think about having a positive result. Science is not about having a straight line always. Okay, science is about having the results and interpreting that results into the interpreting those results according to the scientific principles. Okay. So I would happily display this failure of research in this particular slide, but it is published. And to showcase that, many of my students, they were very, not very happy. Oh, I'm not getting the results. But I always say to everybody, when we are into research, it's all about the results. It's how we interpret those results according to the scientific explanations or scientific principles. So what we did was that we wanted to introduce fluorine in this network. Okay, so thinking that we will have a product which is in which we will have the fluorine incorporated into the final product. But unfortunately, if you see these two slides, this is the finely defined silicon carbide nanofibers. But when we see here, it's everything is collapsed. Okay, so I would have told to my student, no, this is collapsed. This is not a good result. Rather, we sat together and we tried to understand what was the possibilities, how we can say this is a failure, or how we have to tell to the whole world, like, look, we did this mistake and look at the results here. But honestly speaking, it is telling to everybody, like, we did this reaction, but these are the possibilities that while doing the reaction, there is a byproduct which we say it's a hydrogen fluoride, which at the beginning of the reaction, when we did the carbothermal reaction, reacted with the silica and it ate up my silica. So silica was not at all available for further reaction and we got everything collapsed here. However, we could see some kind of nanofibers, here and there in this network, those small lines here, still trying to, exist in the system. Uh, uh, so, but yes, overall, I would say uh, science takes its own time. We need to just understand and explain to the whole world why did it happen. Okay, so let's proceed with the next work which we did was titanium carbide nanomaterial, again using lignocellulosic waste, and we arrived in this beautiful network which was published last to last year, sorry. And it's a beautiful soil gel technology that we made use of again here. And then coming to the technology where these materials which I have developed in my earlier slides can be applied, we can apply onto. So one of the application areas is photocatalysis. Fundamentally, photocatalysis, two terminologies here, photo and catalysis. So any catalysis which happens using sunlight. Okay. Now, when we talk about the catalysis and having the sunlight, the most popular is the titanium oxide, okay, or what we call the titanium. But unfortunately, titanium has its own limitations of being active in certain certain wavelength range of electromagnetic spectrum, mostly between 200 to 400 nanometers of the UV range. So it's what we have to do here now, using solder technology, we functionalize these titania. We incorporate into different materials like rare earth materials or transition metals here, so that these metals can introduce further energy levels, so that all those limitations of rate of recombination or electron hole pair separation and so on we can overcome, and also that the titania itself can be functionalized from 200 to 800 nanometers of electromagnetic spectrum. So this is one of the application areas where we use titania or the solder technology to develop that kind of titanium. Okay, so here is what actually happens with the solder derived titanium or titanium itself. We have this titanium nanocomposite either derived from solder technology or not derived from solder technology. So this titanium, it absorbs the sunlight here, and then we have the valence band here, we have the conduction band here. So what happens when the sunlight falls, the electrons from here, gets excited to the conduction band and leaving behind the holes here. And those electrons then participate in the redox reactions or the reduction process or the oxidation process. On the other hand, the holes participate in the oxidation process here. So this whole process, which is like very quick to view and understand. So I'm just transferring my attention from this particular, graphics to this particular part to make you understand, like when the sunlight falls into this titania, the electrons are here. When the electrons absorbs those sunlight in the UV visible range, they jump up to the conduction band, and then those electrons then react with the oxygen in the medium where the reaction has to take place, and then forms the oxides. And these free radicals or the superoxides further then react with the contaminants to degrade it. And on the other hand, these holes then forms the hydroxyl radical and then do the oxidation reaction on the other part of the soil gel derived semiconductors. All right. So this is one of the published articles where we made use of soil gel technology. What we introduced here were the carbon nanotubes along with this rare earth erbium. And then we found how the photoluminescence shifted, the band gap energies shifted. And then this is the picture of the nanocomposites, the transmission electron micrograph of the soldier-derived nanocomposites here. And then we made use of this particular composite to create organic dyes for our work. Some of the other application areas of soldier-derived ceramics are like water purification. We have a coating on the side mirrors. We have residences, interior in curtain. We have the coating on the curtains. We have agriculture, where the soldier-derived titania have been used for different purposes. The medical field, in the energy sector, the water splitting, the hydrogen evolution, solar cells. So I would say, there are numerous applications based on solar technology. In the medical field, we have the soil gel reagent and how that soil gel process develop the hydroxyapatite deposition in the bone. When we have a fractured bone, let me put it in a simple way. When we break our bones, we have the fracture. Okay, in that particular fracture, whatever is filled in, that component is a combination of the biomolecule and the soil derived, silica. Okay, so this is how in the medical field it is playing a huge role. Then coming to another application areas is like the inks are getting prepared using soil gel technology for 3D printing, and to develop different glass, different the circuits. Okay, using this 3D printed ink. And then I'm not sure if I'm running too fast because I'm worried for the timing.
You have around five more minutes. Yeah.
5 more minutes. Okay, yes. Let me quickly do it. Okay, so next part is the membrane areas that soil gel technology is based. So to put it in a simple way, this membrane, which is like allowing the water to pass through, is made up of the material which are these days made up of, incorporate soil gel derived products here. All right, coming back to the further description, we have the microfiltration membrane. We have different types of membrane, and why we call a membrane a micro or an ultra or a nano, it's because of the size of the product. Okay, so in all these particular different sizes, we are able to incorporate soil gel derived products, to have an ultimate product, what we are looking for. Okay, so finally the summary: easy to handle technique, the sol phase as well as the gel phase we are able to manipulate. Then the technique allow us to have the tailor-made properties. It is a platform to form the nanocomposites. It's a gateway for numerous countless applications. It's a commercially viable technique. All right, so acknowledgements finally to the whole team and the funding agencies, those people who have participated in the work which I have shown. The titanium carbide, Dr. Sedimo Majaki, who has graduated recently with her PhD, Dr. Diseko Bocano, she did the photocatalysis. Donga is doing again something similar. And she's the full fellow. She's doing the soil gel technology for membranes. Nathan finished his PhD with the soil gel derived nanocomposites for adsorption purposes. And finally, I would say thank you all for your kind patience. I hope I made it in time. And welcome for questions.
Yeah, thank you so much, Dr. Shivani Mishra. Thank you. Your lecture was really enlightening. Now you have explained so well that how soil gel technology is very useful in different areas, and it has wide application. Like you started with exosoles, like this is just a kind of new term for me. Like I haven't read about aerogels or different type of gels, but you introduced Zex, what was that? The wet gel and different types of gel. And you explained
Yeah.
up to quantum dots and their application. It was really very interesting. Now, I will take up few questions. There is a question from a student Rajvi. Is the precursor solution, can we use any metal? A question from Rajvi. Or some
Um,
criteria.
well, we, as I said, it's basically the metal oxide, yes, but it has to have some kind of network around it. For example, I can give an example of recently what we did was zinc silicate, like we have zinc, okay, and we have silicate. So some kind of network it should have in its, vicinity, so that it allows the zinc to proceed with the soil gel derived. Zinc itself, if in its pure form, might not be able to go soil gel as such. But I need to have that kind of network, to proceed with soil gel. What is that? I need to have hydrolysis. I need to have polycondensation. Okay. For the hydrolysis, what is the requirement? If I attach that functionality to my metal, so it should be able to undergo, the soil gel process.
Okay, thank you. There is another question from Dr. Abhay Srivastava. He is asking, is the efficiency of soil gel method of nanomaterial synthesis higher over the phytoextract based nanomaterial synthesis?
Um, a fibro extract based. Is it fibro?
Phyto means he's asking about, like, we can use some plant-based material to prepare nanomaterial. So he's asking which method is better. Like you explained about the soil gel method. So why the soil gel method is better than the phyto extract based nanomaterial synthesis, where we can use plant product?
Yes, I mean it's a very good question. Remember that during my talk, what I was speaking about is that soil gel technology gives me an opportunity to, an opportunity to play around the reaction conditions. Okay, if if I choose to have a plant based, okay, so I'm not sure because I haven't done that work, but I'm not sure that if I have that opportunity to nano engineer plant based, nanoparticles or not, because here I can use, different reaction conditions to arrive at different types of network. Okay, so that's the beauty of solar technology. Since I have not worked in plant based, extract, and how we can derive. But what I believe is that because plant-based extracts, most of them have to have hydroxy functionalities, right? If,
Yeah.
let me take up an example of a cellulose or a lignin. Okay, so how beautifully I can think of, uh, uh, using plant extract and do soil gel. That would be very interesting to understand. You know. So yes, there should be a possibility. There should be, but at the moment I might not be able to fully explain because I don't have experience in that particular area.
Yes, you're right. Like without experimental proof, we cannot say which one. Like the phyto product
Yeah,
that we are using for preparation, we may have different properties of the material, so it may have different
yeah,
application, different outcomes.
yeah,
So
yeah. So,
that really need experimental proof to say
yes,
anything
yes,
about this. Yeah.
true.
Thank you.
That's
And
true.
there is one more question from Jishan. He is asking about the role of aerogels in drug delivery system. What is the role of aerogels in drug delivery system?
Um, well, role of aerogel, I have no idea at the moment. But what I can say is that yes, most of the time it is cryogels, which are being used for medical purposes. One thing we have to remember, uh, that when it is has to be a drug delivery, okay, in the drug delivery concept. if I use the cryogel, which is in like the liquidy kind of, form, okay, so it will be easy for the active component to be released, okay. But aerogel, carbon dioxide, first of all, no, not carbon dioxide, sorry, am I messing up with my concepts here? Aerogel, better I would say that I haven't heard of. What I heard of was the cryogel, which are, I mean, in cosmetic industry, in nutraceutical industry, or pharmaceutical industry, people prefer to have the cryogels instead of aerogels because of the liquidity of that, or the mobility uh, of that gel, and the mobility of the active component, which can easily can be released from the network.
Okay. Yes, yes. Thank you, ma'am. Yes, you are right. But I think now people are using aerogels in drug delivery also. I think the application of different kind of gels people are trying in different areas. So
Yes, it's
definitely
possible.
maybe people, yeah,
It's
recently.
possible. It is definitely possible. I
Yeah.
won't say it's not possible, but we need to, again, when we have to, just can't say anything like, it is, we are what we are, uh, what is the concept behind it,
Mm,
why we want to use aerogel.
mm,
So there should be a fundamental concept of using an aerogel for the drug delivery, right? So we need to, define that concept. And yes, there is definitely possibility of. I won't say it's not possible. Yes, people are using. Perhaps I'm not aware at the moment, but what I'm aware of is like more of cryogel than of an aerogel,
mm.
network. So, but
Okay.
yes,
Yeah.
it would be interesting to get further knowledge
Good.
about it.
Yeah.
Yeah.
Thank you. Thank you so much. There are many questions, but we have to like start the another session. So thank you so much. Now I request Dr. Ishwar to say vote of thanks and present e-memento and certificate of appreciation to Dr. Shivani Mishra. Over to you, Dr. Ishwar.
Okay, thank you so much, Dr. Pratibha. Now, it is
One
my
second, sir.
privilege. Yeah,
Sir, 1 second.
yeah, sure.
Shivani ma'am,
Uh,
please stop sharing your screen. Shivani ma'am.
Okay. All right. Okay.
Ishwar sir, now you can continue, Ishwar sir.
Okay, okay. Ma'am, your screen has been stopped because we want to present you the e-memento and e-certificate. Okay, so shortly it will be on the screen. So it is my privilege, ma'am, to propose a vote of thanks to you uh, uh, for introducing us and our young students to the fascinating field of soul gel and its application in the various industries. And so on behalf of Department of Chemistry, Deshbandhu College, and on behalf of entire organizing team and on my own behalf, I would like to extend a vote of thanks to you. And thank you so much, ma'am, for sparing your precious time, because I know you will be very busy. And thank you so much, ma'am, for gracing your important work and sharing with us your great findings and your research work with us, ma'am. Thank you so much, ma'am. This is the
I thank
e-certificate.
thank you for the certificate, and I thank you the organizing committee, because for me it's a very auspicious day, because I have been speaking across the world. It was only my hometown that I'd never presented my work, so it is definitely
Ma'am, it is a
an
pleasure for us,
esteemed
ma'am.
opportunity.
It is
Yeah. Thank
definitely
you
a
so
pleasure
much.
for us. Thank you so
Thank you
much,
so
ma'am.
much. Thank you. Thank you.
Thank you. Thank you so
Over
much.
to you, Ron.
Thank you, Iswa sir. I would like to thank again Dr. Sivani for the exciting and interesting talks about social technology in its wide applications. I would also like to thank again Dr. Iswar Dutt for chairing the sessions and Dr. Pratibha for hosting the Q&A sessions. Now, I would like to kindly request Dr. Aparna Sekhar, Assistant Professor, Department of Chemistry, Deshbandhu College, to kindly invite and introduce the second speakers for these sessions, Dr. Sumati Bhatia, to the audience. Over to you, Dr. Aparna.
You're not audible, ma'am.
Dr.
Am I
Sumati
audible now?
Yes, yes, you're audible, ma'am. Yeah.
Okay, okay.
Thank you.
Thank you, Marco. Indeed, it is a matter of great privilege and honor to introduce the speaker, Dr. Sumati Bhatia, whom I happen to teach in post-graduation in University of Delhi. A hardworking and sincere student, as I still remember her. Dr. Bhatia leads a research group in developing polymer-based materials to combat viral and bacterial infections at Free University, Berlin. She did her PhD in chemistry from University of Delhi and then her postdoctoral research at Free University, Berlin. She has published more than 39 research papers and articles in highly reputed journals and owns 2 granted patents. She has been awarded Printing Award from German Science Foundation and also has been shortlisted for Raymond Stadler Prize in Germany. She is also principal investigator in Corona Pre-Exploration Project of Berlin University Alliance. So without wasting much time, may I now invite Dr. Sumati Bhatia to address the participants. Over to Dr. Bhatia.
Thank you very much, ma'am. I was not aware that you will be here today. It's am I audible to everyone?
Yes, you're
Sumati, you
audible.
are audible.
Okay, okay, nice. So it's a really great surprise, and I'm really happy to see you here today also. Yeah, although online. So as ma'am said that I have done PhD also from Department of Chemistry, University of Delhi. So it's always a great pleasure to be here and share my research work with all of you and also with all students. Yeah. So maybe I just start with my presentation and then we talk later again a little bit more about my stay in Delhi University. Is my presentation visible to all
Yes,
of
Sumati,
you?
it is visible.
Okay, nice. So as we all know that we are these days passing through this pandemic time of Corona, and we really hope that it's ending after Omicron and it's getting milder and milder with the new strains. So past few years also, I have been working to meet the challenge of viruses, and I was developing some polymer-based materials to respond to viral infections. So as you can see on the right-hand side of my slide, so this ball, this green or golden color ball, you can consider as virus particles. And you see that there are different kinds of polymer-based materials which are entangling these virus particles or which are entrapping these virus particles. So maybe, okay. So for example, here you see this is a random coiled linear polymer, which is wrapping around the virus particle. And then here you see a dendritic polymer, which is also binding with the multivalently binding with the virus particle. And at the bottom, you see a gel-like structure. So a gel which is just settling down on the virus particle. So we can really respond to these viruses in different ways by preparing different polymer-based materials and optimizing these polymer-based materials to either stop the infection or interfere with the infection at late stages or to block the viruses or to trap the viruses. So I will discuss some of these aspects in my presentation today. And before jumping to viruses, I would like to introduce the concept of multivalency in our daily life because that plays an important role in viral infections as well. So multivalency, as the name suggests, it means the different ligands are presented in a multivalent fashion on a surface, right? So for example, you might have seen this dried seed called burr, which has these needle-like structure distributed on its surface in a multivalent fashion. So this is the best example of multivalency, which you can see in a garden or in day-to-day life. And the best example of multivalent interaction is a Velcro. So you see on the right-hand side, this is a Velcro, which has tentacles and hooks, which are bound together by multivalent interactions. So you can close it and then it is quite firm. And then you can open it up also by applying force. So what I mean to say that multivalent interactions can be strong, but they are reversible. So for such multivalent interactions, you don't need covalent bond to get formed. So they can be reversible yet strong. And also for the multivalent interaction, the basic aspect to be fulfilled is that M and N should be greater than 1. So on both sides, ligands or receptors, they should be greater than 1. So there should be at least 2 receptors and 2 ligands which are able to bind together. So this is the example of multivalency in day-to-day life. And then we go to the viral infections, viruses, viral or bacterial infections. How does it happen? So we all know cell is the basic unit of life, right? So if viruses are infecting us, that means that viruses are infecting our cells. So our cells are getting infected, right? So on the left side, you see this ball again, which for this presentation, you consider this as a virus. And on the bottom, you see this cell surface, which has a lot of receptors like shown here as the red balls, right? And the virus just adhere on this cell surface through multivalent interaction. So virus cannot bind with the cell with a single ligand receptor interaction. They have to be multivalent. That's why they have to be strong. So one can think of why not to interfere with this in this first step of infection. So one can think of, okay, we can design a single drug which is mimicking these receptors, like shown here as red ball. And this single drug can accommodate a lot of glycoproteins, and then probably it is able to interfere with the first step of infections. So first of all, if we design such a drug molecule, and these drugs are already known, are already commercially available, first of all, we need very high concentration of these drug molecules to get bound with all these glycoproteins on the virus surface. And at such high concentrations, they become cytotoxic as well. And the second thing, even if we design a single drug molecule which can accommodate a lot of glycoprotein on the virus surface, but still it will never be able to completely inhibit this first step of infection. So to completely block this first step of infection, one can think of developing a multivalent ligand, which has those such drug molecules presented on this polymer backbone in an optimized fashion. And when this polymer backbone does not only bind with lot of glycoproteins on the virus, but it also sterically shields the virus so that it can completely block this first step of infection. So this is an idea to develop a poly-based multivalent scaffold to interfere with this first step of infection. So in the talk today, I will not focus on corona, but I will focus on the influenza virus, where I have been working past few years. So let us introduce the virus first. So you see this virus here. So we have seen SARS-CoV-2 has caused so much pandemic in past 3 years already. So we are passing through the third year of this pandemic wave. But in the past several years, influenza have always caused epidemic and pandemic in the society. Maybe you all remember the 2009 swine flu. It was declared as a world global pandemic in 2009 also, and then in 2011 also. So there are 500,000 deaths every year because of this influenza infection. Influenza also have high mutation like corona, right? So they once go into the body and then they come out as a different personality. So they mutate really fast. So there are a number of influenza strains already known, already clinically investigated and clinically identified. And the corona and this influenza, within these many years, it has also developed a drug resistant. So the drugs which are already available in the market, like Tamiflu, amantadine, rimentadine, there are strains which are resistant to these drugs already. So influenza mutates also quite fast. And mortality rate is high in high risk patients, like immunocompromised patients. They have already severe diseases or passing through severe disease problems for several years, or babies or elderly patients. Yeah, they are all really, mortality rate is quite high in those patients. Now, if you look at the surface of the influenza virus, so first of all, influenza is pleomorphic in nature. So it can be spherical and it can be elongated as well. And on the surface of the virus, there are two types of glycoproteins. So there are hemagglutinin primers, as you see here in the brown. So they are trimers. So you see the image of this glycoprotein. So it has a head domain, globular domain, and a stem domain. And on the top of the globular domain, it has 3 binding sites. And these 3 binding sites have receptors for sialic acid. So sialic acid is a sugar molecule. And there is also another glycoprotein which is tetrameric in nature, but we will come to this again later. First, we focus on this hemagglutinin glycoprotein. So this hemagglutinin glycoproteins have 3 binding sites, and these 3 binding sites have receptors for sialic acid. And these sialic acid is the most exposed sugar on the cell surface. So you see now these red small balls which are expressed on the cell surface. And the hemagglutinin with this, and the influenza virus with its trimeric glycoprotein that is called hemagglutinin, this binds with the cell through multivalent interaction. So the first step is the adhesion, and then it's how the first virus rolled down on the cell surface, and then it found that position where it can bind strongly by multivalent interactions, and then it goes into the cell by endocytosis, and then the infection starts. So we can consider this adhesion as the first step of infection. And then the idea is to interfere this first step of infection by optimizing a polymer-based drug or a polymer-based multivalent drug molecule, which can mimic some aspects of the cell surface. At least it can mimic in terms of the sialic acid density, and then the virus will bind to this polymer but not with the cell. And then we are able to stop the infection at early stages. And the cell surface density of sialic acid is already known, like there are 50 to 200 sialic acid per 100 nanometers square of the cell surface. So 0.5 to 2 sialic acid per nanometer square of the cell surface present. And this is very important for the design of the polymer scaffold, because we want to have more or less the same density of sialic acid on our polymer scaffold. Now, this inhibition concept is not new. So this was introduced in 1991 by Whitesides in MIT. So they proposed 2 different types of inhibition mechanism. So they say if we design a linear polymer scaffold, as you see here, which is decorated with these sialic acid ligands, so either it can bind with most of the glycoproteins on the virus surface, and the virus and cell binding adhesion is inhibited, or it can also not only bind but also coiled around the virus surface, so that it is, even if it is not binding with all the glycoproteins, but it is somehow shielding the virus surface from binding with the cell. So there are 2 different types of mechanism they proposed, and they said depending on the optimization of this scaffold or depending on the nature of the scaffold, both are possible. So what we want to do, so after that they developed a linear polyacrylamide based sialosides, which were really good, which were nanomolar binders, but they had limited biocompatibility. So no multivalent such scaffold could be investigated in vivo or for the development of the drug molecules. And then there were also some reports which explored dendritic scaffold, and they decorated most of the surface with the sialosides, and they could achieve like 50 to 170 fold more active inhibition, but they were not highly potent and they were not broadly active. So there were some abstract studies in literature already. Some were on linear, some were on dendritic, and some were also there on low valent molecule like 5, 6, 7, 8, something like that. So what we wanted to address in our project, so we wanted to develop such a candidate which has optimum ligand density. So here ligand means sialic acid, which have optimum ligand density. So if you put unnecessary more and more ligand, the molecular weight of the polymer gets bigger, and then it cannot be cleared through kidneys. Then it itself is a problem. So you don't want a molecular weight to be above 40 to 60. So kidney clearance threshold for any polymer or for any drug molecule is around 40 to 60 kDa. So the better if we stay within 40 to 60 kDa molecular weight. So kDa means kilodalton. Yeah, 60 kDa means 60,000 gram per mole molecular weight. So we wanted to have an optimized ligand density. So we wanted to have optimum sialic acid, which is just enough to bind strongly with the virus. We wanted to stay in the low molecular weight, which is 40 to 60 kDa, or size which is up to 12 nanometer for the kidney clearance. We wanted to develop a candidate which is broadly active. So influenza has so many strains, H1N1, H3N2, H1N7. So there are so many different strains of influenza there. And that candidate should be active against most of the strains. Then only it is useful. It has to be highly efficient. So it has to be highly potent. So it should be active at very, very low concentration. So you don't need to have very high concentration of that polymer scaffold. And also it should be scalable. So you should be able to scale up that system. And in the end, it should have high biocompatibility. So we wanted to develop an architecture which is eligible for in vivo application. And for its eligibility for in vivo application, it should fulfill for all these, should fulfill all these criteria. So the question was, so there are different polymer geometries known. There are different types of topology of polymers known, but the basic geometry is linear or dendritic. So the question was whether we choose a linear, like Whiteside's proposed, or we choose a dendritic, because there are clear pros and cons of linear and dendritic polymer scaffolds. For example, if you choose a linear polymer scaffold, it will coil, yeah, and when it's coil around, lot of ligands, like for here sialic acid, will be hidden inside the coils, so they are not exposed to interact with the viruses. So anyhow, you need to put much higher density of sialic acid on such a linear polymer backbone. So you need a high ligand density, relatively high ligand density, and all ligands are not available for binding with the virus. Second option is a dendritic scaffold where all the ligands are exposed, and probably you need much less density of sialic acid because all are exposed on the surface, all are available for binding with the virus. So you need less sialic. So here ligands are much more exposed, here ligands are less exposed. But the flexible ligand, which is a linear, so linear is more flexible than the dendritic, right? Because linear is a random coiled polymer, it is more flexible. But probably linear, even if we need high ligand density, it can sterically shield the virus surface better. It can shield the virus surface from binding with the cell better, and maybe then it is much better than the dendritic scaffold. So we did not know this, and this has never been studied in detail. So what we did is we have chosen two polymer scaffold. One is linear polyglycerol. So you can see a small glycerol unit, monomer unit. So it's a polyglycerol, which is prepared by anionic ring opening polymerization of the glycerol. And it can be prepared in several gram scale. So scalability is not a problem either for the linear or the dendritic. And then we have chosen a dendritic scaffold. Yeah, and both are chemically similar because this is also a polyglycerol, this is also a polyglycerol, but this is dendritic and this is linear. And then we prepare different densities of sialic acid on these linear and dendritic scaffold. So for example, here the synthesis is shown for a dendritic scaffold. So this is dendritic polyglycerol. So you can see a smaller monomer unit is a glycerol everywhere. So we have chosen two different molecular weight. One is 10 kDa and one is 500 kDa. And in few steps, we could prepare the different sialosides on these dendritic polymers. Like this is 10 and 500 kDa. First step is the mesylation. And mesyl is a good leaving group, which can be replaced with the azide by reaction with sodium azide. And then we do a click with the sialic acid, propurgulated sialic acid, which can be prepared in 6 steps of synthesis. And then one can do copper assisted click to form these dendritic polyglycerol sialoside. And then you can control the degree of methylation here by putting different molar ratios of the methyl fluoride. And then, for example, if you have obtained 10% methyl, then you will automatically obtain 10% azide, and then in the end, you will obtain 10% sialocyde. So one can control the ligand density by the first step itself. And this ligand density can be easily determined by the integrals in the NMR. So there are very clear peaks for this CH2 and for this CH2 at the C3 position. So one can clearly integrate the sialic acid integration with respect to the polymer backbone in the NMR. And you can prepare different degree of functionalization on this dendritic polyglycerol. So we prepared different range, different like 5%, 20%, 40%, 90% on 2 different backbones. And in the same way, we prepared these linear polyglycerol sialosides as well. So there could be 2 ways. One is that you took this linear polyglycerol and then do the allylation and then prepare this thiol sialic acid and do thiol click to form the different sialoside. And one can also follow the similar route like methylation, azidation, and azide alkyne click to achieve these different linear polyglycerol sialosides. So here also we prepare different densities of sialic acid on the linear polyglycerol. So in the end, we had all these compounds prepared, and then one can determine the hydrodynamic diameter of all these polymer scaffold, right? So this is like, now you see, so here are the linear polyglycerol with increasing sialic acid density, like 10%, 40%, 70%, 100%. And then here it is 10 kDa and 500 kDa dendritic polyglycerol, like from 5% to 90%, and then from 5% to 70%. And if we look at the hydrodynamic diameter, so hydrodynamic diameter one can obtain from the dynamic light scattering, which is a very common technique, to determine the size of different particles when they are dispersed in water or in any other solvent. So because all the particles dispersed in a solvent, they have Brownian motion. Yeah, and then if you can track their speed somehow, and then you can determine the diffusion coefficient, so the machine can tell you by applying Stock-Einstein equation what is the hydrodynamic diameter of these particles. So here you see that in case of linear polyglycerol, the size increased from 7 to 11 nanometer. And this is 10 kDa polymer backbone. And with the 10 kDa similar molecular weight polymer backbone, the size increased from 6 to 9 nanometer. And similarly for 500 kDa, which is a much bigger polymer backbone, size increased from 12 to 14 nanometer. So if we compare 10 kDa LPG and 10 kDa DPG, linear and dendritic, we see the increase in size, increase in the hydrodynamic diameter of linear polyglycerol is much higher than the increase of DPG, which shows that LPG swells more in water, and it was expected also, right? And here we see the increase in size only because of the hydrodynamic shell. And here we see the increase in size because of the swelling of the whole polymer backbone. So LPG swells more. And in fact, the size of LPG, if we look at these 10, 11, they are more or less in the same range of 500 kDa polymer. So this means this 10 kDa LPG is competing well with the 500 kDa DPG, even if it's only 10 kDa, very, very small molecular weight in terms of polymer. Still, it is competing well with such a big molecular weight of the dendritic scaffold. Then we just did a computer-aided design to see how many receptors these dendritic or linear polymers can be in contact. So it's without water, it's just a computer edit up to the size. So the dimensions have been taken care of, that's all. So we don't know when polymer will really interact with the virus, how much it will deform. So one can simulate a little bit on that, but we are unable to see that because these compounds have very, very low contrast in cryotemp. So we cannot really see them deforming on the virus surface. But what one could expect and one could anticipate, because we know the the hemagglutinin distribution on the virus surface. So this is the cryo-electron microscopy image of the virus, and these dark black dots are actually hemagglutinin glycoproteins. And you see the difference between the two hemagglutinin glycoproteins is up to 12 nanometer. And the difference between the two receptors is already known in literature, that is around 4 to 6 nanometer. Okay, and there are 600 to 1200 hemagglutinin primers per particles, and they are distributed uniformly on the virus surface. Now, if we take the 10 kDa polymer, it can interact with maximum 2 different receptors at 2 different primers. 500 kDa can interact with the 3 different receptors at 3 different primers. And the linear polymer, which is swelling more, it can interact with 3 different receptors at 3 different primers, right? So this means this 10 kDa LPG is competing well with the 500 kDa dendritic polyglycerol. So next step was to screen all these compounds. And what we did for screening, we did the hemagglutinin inhibition. And this is a very basic assay one can do in the lab. It's quite simple. So I just explained the mechanism first and then the result. So we screen all these compounds in a hemagglutination inhibition test. So what is hemagglutination inhibition test? So this is related to the red blood cells, because red blood cells also express a lot of sialic acid on their surface. So if we have red blood cells in a tube, in a test tube, let's say, so after some time you will see they just agglutinate, they just interact with each other and form a pallet at the bottom, right? But if there are viruses present with the red blood cells, viruses, because they interact with the sialic acid, they interact with the cells, they will interact with the red blood cells, and red blood cells will not form a pallet, but it will be shown as a smear, like a spreaded gel type structure on the surface. And now if you have an antibody or an inhibitor which can bind with the viruses and which can inhibit the viruses from binding with the cells, then you again see a pallet, right? So this means if we use different concentrations of the inhibitors, and then we see when the first pallet gets formed, and then from there we can get the inhibitory concentration of our inhibitor, right? So with this assay, we can easily determine what is the minimum concentration of the inhibitor required to form a pallet again, or required to do the inhibition, or to do the hemagglutination inhibition, right? So we screened all these compounds in hemagglutination inhibition test with different concentration, and this is the result of that. So y-axis, you see the minimum concentration of the inhibitor required from that compound, yeah, to do the hemagglutination inhibition. And on the x-axis, you see the sialic acid density. So we prepared these 3 different series with different sialic acid densities. So for example, in the red, you see the 10 kDa DPG, and you see, okay, 10%, for 10% concentration was high. For 20% scaffold, for 20% sialoside, the concentration was lower. 30% was little higher, 60% was down. And if you go with the higher density, it is much higher again. So that means the optimal minimum sialic acid density on the 10 kDa DPG should be around 20%, 15 to 20%. And the same was for the 500 kDa DPG. So for 500 kDa DPG also around 20%, we need a minimum concentration. We need a very low concentration of the 20%. So 20% performed best in the hemagglutination test. And for the 10 kDa also 20% performed best for the hemagglutination inhibition. And if you see the LPG linear polymer, as I told you already, that for a linear scaffold, sialic acid density should be much more, because a lot of sialic acid is hidden inside the coil. So here you see the sialic acid density ranges from 40 to 70%, around 40 to 70%. So we choose these 4 compounds where the concentration required for the hemagglutination inhibition was minimum. Yeah, and then we screened these 4 compounds in different tests. So first is the MST, which is a micro scale thermophoresis technique. So first we wanted to see how much affinity of these scaffold are with the virus. So affinity is determined in terms of KD value, dissociation constant. So how strongly an inhibitor can bind. So lower the KD, higher is the inhibition, higher is the binding. So these are 4 compounds, 40%, 70%, and the middle point tells you the KD value, right? So here is, so on y-axis you see a fluorescence change. So here what we do, we take the virus particles which are fluorescently labeled, and then we incubate those virus particles with different concentrations of the inhibitor, with different dilutions of the inhibitor. And the light is thrown on these tubes, and then with the energy gained from that light, these bound or unbound particles starts dispersed. And then you see a fluorescence change. And from this fluorescence change, and you can plot this fluorescence change with respect to the concentration. And the middle point tells you the KD value. So this is relatively a new technique, this microscale thermophoresis. But I would ask you to focus on this table, which tells you a very important information. So here you see the Ki values for these 4 inhibitors obtained from the hemagglutination inhibition test, where the inhibition was done in presence of cells, where the virus was inhibited to bind with the cell in presence of these inhibitors. And here you see the affinity values, yeah, KD values for these inhibitors with the virus, where there are no cells, right? So now if you compare any 2 compounds which have almost similar KD values, and then you see their Ki values, and then you see there are some additional effects incorporated with the LPG. For example, if you see these 2 values in red, this is one is 10 kDa LPG, 0.6 micromolar KD value, and then another is 10 kDa DPG, 1.46 micromolar KD value. And if we consider this plus minus values, KD values are more or less same. There is not much difference in the KD values, 0.6 and 1.4. But if you look at the Ki value, these are obtained from the hemagglutination inhibition. You see the LPG Ki value for the LPG is 6 times lower than the 10 kDa DPG. So although these 2 compounds have more or less the same affinity, LPG works much better than the dendritic analog in the cell binding inhibition, in virus cell binding inhibition. That means there is higher steric shielding contribution by LPG rather than DPG. And without compromising much on the binding affinity, it sterically shields the virus better. So you can anticipate the steric shielding contribution by linear polyglycerols here by comparing these 2 different assays. So far we knew, okay, LPG sterically shield the virus surface better, okay. And now what we did different types of tests, but I don't want to go into all those infection tests. But finally, we brought 3 compounds into the in vivo, into the mouse model. So let me tell you, it is still a prophylactic test. So where the compounds are incubated with the virus first, and then they are incubated into the mouse nose. And on the x-axis, so first of all, no mouse died because of any acute toxicity. So these compounds were not toxic. And then here you see on the y-axis percentage of the initial body weight of the mouse. So you see how much body weight of the mouse decreased because of the infection. And on the x-axis, you see different compounds. And you see the green one show the LPG compound, where the body of the mouse body weight of the mouse decreased only 2 to 3%. Where in case of DPG compound, it decreased a little bit more. And OC is the oseltamivir carboxylate, which is a commercially available drug, where the body weight of the mouse decreased up to 8%. So all these LPG or DPG compounds were much better than the oseltamivir carboxylate. And if you compare the LPG and DPG, LPG works the best. And when we used LPG with the oseltamivir carboxylate, we saw a synergistic effect. So no mouse decreased, all the mouse remained almost healthy. So this LPG compound outperformed the DPG analogs, and this LPG compound was even better than the oseltamivir carboxylate. So we published this paper in Biomaterials, and also we got a granted patent application. But the story did not stop here. I hope I still have enough time to show you some more slides.
Yes, ma'am, you have around 10 minutes.
Okay. So this thank you. So this LPG compound was good, but it was not broadly active. So I told you there are different strains. So this LPG compound was active against only this X31 strain, which is mouse adapted strain, which is not uh, for human. So this was not broadly active. So our idea was to develop a broadly active candidate. So if we look at the cell surface composition, on the cell surface, there are different glycocalyx. So there are, so on the tip, you see the sialic acids. But sialic acid are not present as a single sugar molecule. They are always present as sialylactose. At least the next unit is the galactose. And you see here a specificity, different receptors on the birds and in the human. So for example, in the birds, they are infected with the avian influenza, and then there is a receptor binding. So actual receptor is the alpha-2,3 sialic acid here, 2,3 sialylactose. And when this virus goes from birds to human, the receptor specificity changes. So in the upper human respiratory tract, the sialic acid is present as 2,6 sialylactose. And in the down respiratory tract, lower respiratory tract, it is present as 2,3 sialylactose. So our first idea was to replace sialic acid with the sialylactose. At least from the first story, we got an idea about the architecture that LPG is better. And now the goal is to change the ligand into a broadly active ligand. So what we did, we used the sialylactose instead of sialic acid and converted into the different derivatives. And these different derivatives were coupled with the LPG, and we prepared the LPG sialylactose. And then we screen all these LPG sialylactose against different strains. And here I will ask you to focus on this light blue bar. So this light blue bar is the sialylactose, LPG-26 sialylactose. And you see, and on the x-axis, you see the virus titer. Lower the virus titer, more active is the compound. So these are controls. And then here you see that this blue bar, this is always much down. So this LPG sialylactose was broadly active, although it was not active against the PR strain. But against some of the strain, it was active. But still, we needed a 5 micromolar concentration of this compound. Although we got some broad activity, and some of these results were published in JMedChem also last year, but this compound was not highly potent. So our idea was to prepare a highly potent compound, which is broadly active and highly potent as well. Then what we did do, then we need to look at the virus infection assays. So till now we looked at only how the virus bind with the cells. Only we looked at this, right? And now what we wanted to focus on how the virus is released from the cells. And the virus is released to release the new viral particles from the cell surface, the shallow side bonds needs to be cleaved. And to cleave these shallow side bonds, we have neuraminidase on the virus surface. And then there is a neuraminidase binder known, which is also a commercially available drug against influenza, which is zanamivir. So if you get severe flu, you have to take 4 times a day. You have to inhale this drug 4 times a day. So of course, very high concentration of this drug is needed. So this zanamivir can bind with the neuraminases. So what we thought now, that we will prepare a linear scaffold which does not present only sialic acid, which also presents zanamivir on its polymer backbone. And thus, such polymer scaffold does not only inhibit the virus entry, but they also block the virus release from the cell surface. So you see these polymer chains are entangled around the virus surface. They are blocking the entry, and now they are blocking the release also because they have optimal zanamivir on their surface. So I will not go into these synthesis because then we prepared different backbones with sialic acid and zanamivir compounds. So these are the results, but I would ask you to focus on this table. So these are 3 different strains, yeah, and these, for example, this H1N19 is the pandemic strain in 2009, which caused a worldwide pandemic in 2009. And you see these different polymer scaffold, and zanamivir is the commercial available drug. And you see the IC50 value of these zanamivir, which are quite high, like 7 micromolar, 44 micromolar, 135 micromolar. And if you see our optimized candidate, it has IC50 values much lower, in very low nanomolar range, or we can say more or less in picomolar range. So we see this optimal compound outperform the commercially available zanamivir drug also under these experimental settings. And these are post-infection tests. So cells are already infected with the virus, and then these compounds are brought into the picture. So like we take drugs when we are already infected with the virus. So we developed a candidate which is much more active than the zanamivir commercially available drug and all our other previous candidates as well. And this is also a test in the human lung tissue culture model. So we obtain lung from the clinical patients, so healthy lung parts, and then it is cut into the small pieces, it is infected with the virus, and then these compounds are incubated these compounds are incubated into the solution with the lungs and the virus. And if you focus on this yellow curves, the lower the y-axis values, lower is the infection. If you see this orange curve, which is our optimal compound, this is behaving best than all other compounds, even for the infection in the human lung ex vivo. And you see here the zanamivir drug, which is used at much higher concentration than our compound. And here still the infection is getting increased. But here the infection reached a plateau. So this compound worked even better in the human lung also against this as compared to this commercially available drug. So this hopefully this paper we will submit this year. And then I just wanted to show you a little bit more story. So all these polymer scaffold were inhibiting the virus at earlier lots, late stages of infection. But you can imagine if you have infection. So for example, in case of corona, in the initial phase of pandemic, we all knew and we all read that this virus first stay in the throat for 3-4 days, and then it reaches to the lung. So if we have a virus which is growing into the throat, then you can think of a gel solution which you can use to gargle out, and then these gel solution, if they have such gels which can really block and trap the viruses, and then you can get rid of all those viruses at initial stages. So here we prepared gel compounds. So I will not go into the technology too much here because of limited time. But we prepare these 3 different types of gels as we showed at the down. R stands for rigid, F stands for flexible. So rigid gel and flexible gel. And these red are the ligands, sialocyde ligands, which are presented on the linear polymer backbone or on the dendritic or the spherical backbone. So these linear polymer backbone incorporates more flexibility to these gel compounds, right? And we determine the flexibility. These flexible were able to deform more than the rigid. We determine the size by DLS and also infection inhibition. So the flexible nanogel, which were presenting sialic acid on the linear chain, it showed the good infection inhibition in picomolar concentration. But amazing picture we obtained from the cryo-TEM that you see here. This is the virus, influenza virus. And here you see a nanogel which is deforming at the interface of the virus. You can see the clear deformation of these nanogel at the interface of the virus. So which was really interesting and really motivating, such pictures. So hardly we could see such pictures with our compounds actually. So we could prove that these flexible gels are more active because they are able to just settle down. They are able to just adapt on the virus surface. So they are designed in such a way, or their flexibilities are designed in such a way that by multivalent interaction with the virus surface, they are able to adapt on the virus surface. So at least I could show you that we need an optimal ligand presentation. So we could achieve high efficiency with our mixed multivalent system. We stayed in the low molecular weight, small size. We could achieve broad antiviral activity. These polymers are highly biocompatible. They are scalable. And then in the end, we could also formulate with these polymers an IAV blocker, which can adapt on the virus surface. Then, of course, I should acknowledge my co-workers for electron microscopy, for ex vivo studies, for antiviral activities, for in vivo. So in vivo was done in the Harv Hammond group, and then antiviral activity, Marina did some antiviral activities from the Robert Koch Institute, and ex vivo were done in the hospital by Morris and Katia. And of course, I also thank my funding agencies like SFB 765, Berlin University Alliance now for Corona project, and also my independent funding from the DFG to run my own group, and also collaborators from different institutes. So it is not possible without this cooperation, of course. And thank you very much for your attention. And and thank you very much for the organization and invitation. And if you have further questions, please go ahead.
Thank you so much, Dr. Bhatia. Your lecture was very informative, and we really enjoyed your lecture. And now I'm taking up few questions. So there is a question like, please explain the factors that need to be kept in mind while choosing polymer composite to bind with any biomolecule. This is the question from Deepa Sharma.
Okay, that's a very good question. So first of all, you need to think about the target. I mean, that totally depends what target you're choosing. How big is it? How small is it? If the receptor binding pockets are hidden or they are exposed, so you need to think about. So you really need to have a good knowledge about the target. So first of all, you would focus on the receptor binding pocket, and you need to know the ligands, which ligand can bind to the receptor binding pockets, because in the end, you will present those ligands on the polymer. And there is always a debate whether to choose a linear or a dendritic, whether to choose a stiff or a flexible scaffold. So because there are a lot of theories now behind linear flexibility. So flexibility on one sense, it is quite good, because you can, if for example, if you see the receptor binding pockets are hidden in the biomolecules, they are not quite exposed, then you need to incorporate a little bit flexibility into your system so that the ligand can reach those binding pockets, even if they are hidden. Because otherwise, if your scaffold is too stiff and the receptor binding pockets are hidden, you will never be able to bind them, right? So first of all, if it's hidden, you will incorporate a little bit flexibility, but flexibility, and with flexibility, even if the binding is little less with the flexibility, but still you are able to reach the binding pocket, that is always a plus point. But on the other side, if you see the ligands are quite exposed and it's really easy to reach those binding pockets, then I would suggest not to choose any flexible scaffold. Choose a rigid one, because rigidity always brings high binding. And flexibility always, there is an entropic cost and you lose the binding affinity because of the flexibility. So that totally depends where you want to bind, how the receptor binding pockets are exposed, how is the topology of those receptor binding pocket. And one more important thing is this, whether the receptors are present as monomer, trimers, or dimers. And then you need to know what are the dimensions of these receptors, what is the differences what are the size span of these receptors. Because to incorporate the concept of multivalency by a polymer scaffold, at least you would choose that much big size, which can accommodate at least two receptors at the same time. Because if it is so small and it is able to bind only one receptor, then you will not be having benefit of the multivalent interactions. So I mean, there are so many papers behind this, how to choose a receptor, what ligand, what kind of linker you should choose, what kind of polymer you should choose. I mean, if receptors are quite exposed, one can also think of just using nanoparticles. You don't need to go into the complication of polymers then. Yeah.
Oh, thank you so much for beautifully explaining all the aspects. Now I have a query, like whenever we talk about polymer as therapeutic or as drug delivery system, it's always we prefer the polymers having many oxygen functionalities. Mostly there is oxygen in the polymer or any polymeric material which is taken as therapeutic or drug delivery system. Why is it so that there is mostly oxygen functionality? Like, why oxygen is so important?
Oh, okay. So, okay, let me choose two polymers to answer this question. I mean, it's very difficult to say something straight on that. So instead of oxygen, I would suggest that you look into the functionality. Either it is present as an ether or carbonate or ester. Oxygen is required for all these different functionalities, right? Or you can imagine a you can imagine a peptide which has amide bonds, right? So what we saw that if you choose a peptide are a little bit more immunogenic than the esters or ethers or carbonates where oxygen is incorporated. So if you want to, either you choose a peptide or a polyacrylamide, which I showed, which Whitesides used, they are also amides bond, but they are not highly biocompatible, first of all. So you will stay away from the peptide until unless it is absolutely needed. Yeah. And then you come to all these functionalities. So if we consider ether, ester, carbonate, all have oxygens, first of all. Yeah. So in a way, all these functionalities will be, all these polyfunctional polymers will have oxygen. Yeah. So or you choose polysaccharides, they also have oxygen. So I think this is the gift from nature that mostly all the biocompatible polymers have oxygen, because oxygen also brings degradability of the polymer inside. For example, if it is ester, so in the end, you want a system which will degrade in the end. So you don't want a system which will accumulate in the body, right? So if we consider polyester, they are degradable. Polycarbonate, they are degradable. Polyethers, they are not easily degradable, but there are some reports that superoxide anions, which are released from macrophages, they can lead to enzymatic degradation of those polymers as well. Or in case of polyethers, we try to stay within the size limit of 40 to 60 kDa. But it is known polyesters will degrade in the body, polycarbonates will also degrade in the body, polysaccharides will also degrade in the body. So in the end, you have a better degradable system when there is oxygen into the polymer backbone. So peptides will also degrade, but peptides will be a little bit more immunogenic. So you will you will try not to use them, right?
Thank you so much. Like, I think you explained so well, like whenever we have oxygen, so we'll not get any, it's the biodegradability that may be very important factor for oxygen. And when we have nitrogen, there may be ammonia, so that may produce in high concentration. So that may be the reason that we prefer oxygen functionality more. That could be the reason. The biodegradability is, I think, is very important for any type of drug that
Yes.
we are planning to design. Thank you so
Yes,
much,
of
Doctor,
course.
for taking all the questions, all the queries. Now I request Dr. Aparna Shekhar for the vote of thanks. Dr. Aparna Shekhar.
Thank you, Dr. Sumati, for such a nicely present and informative session. On behalf of Department of Chemistry at Deshbandhu College, I take this opportunity to present you with an e-memento and an e-appreciation certificate as a token of gratitude. And hope to see you in person sometime once pandemic stabilizes. And thank you once again for sparing your time and joining us in this symposium. Thank you very much, Dr. Sumati Bhatia.
So I must say this is like a big pleasure for me also to present here, because there are so many memories I have from my master time and from my PhD time and also bachelor time I have spent there with my friends and my teachers and professors and with you also. So yeah, so it was a great pleasure to present here, and I really enjoyed, and such a huge crowd. I did not expect that there will be 300 students. I mean, total 300 people, yeah, listening to the talk. So this is quite amazing. So thank you, Pratibha, also for kind invitation, and thank you also you, Aparna ma'am, and then thank you all thank you the whole organizing committee for organizing such a great session on different topics. Yeah, I also really enjoyed. So I could not join all the talks, but at least a little bit of the last talk, which I also really enjoyed.
Thank you so much, Sumati.
Thank you very much.
Thank you. Thank you so much.
Thank you, Dr. Aparna. Thank you, Dr. Sumati, for the wonderful talk and then enlightening us about the concept of multivalency and the use of polymer-based materials for combating pathogens. I would also like to thank Dr. Pratibha for hosting the Q&A sessions. Now we have, with that, we have concluded session 2, and I would like to thank all the audience for actively participating in the second sessions. The next section will be quiz sessions, which will be at 3:30. But before that, we'll have a very, very short break for 10 minutes. And then before that, I would just like to make one important announcement. The feedback link will be provided in the chat box. So it's very important for the participants to fill it up, the feedback form, so that they will get the certificate. So we'll have a very, very short break, and then I'll hand over the time to the quiz coordinator. Thank you.
So dear participants, don't leave the session. We will start at 3:30 sharp with the quiz. So you all can participate in the quiz sharp 3:30.
एक वीडियो चला दो कुछ प्रतिभा
Leena,
हाँ वो
Dr.
अभी
Leena, please play some video.
So welcome back to the last session. Good afternoon to all. Am I audible?
Yes,
Yes,
sir, you
sir.
are.
Okay. So after the informational and technical sessions, we have come to the last session, which is I call a fun session for the students. So I will coordinate the quiz for today's symposium. So there are some rules for the quiz. Dr. Lina, can you please present on the screen? So these are the rules for the quiz. There are 20 questions and you have to complete them within 10 minutes. There will be 3 winners, and in case of any tie, the participants who will submit first, he will or she will be the winner. And we will not be responsible for a delay in submission, which is due to any technical glitch or your slow internet connection. And the link for the Google form will be given in your chat box, and I am sharing that in your chat box. You can use from there. Okay. So I have shared the link, and time also has been started. So it will automatically stop after 10 minutes.
Yes, all students can participate. All participants. This is for all participants. You just have 10 minutes time and you have 20 questions. So hurry up.
Okay, thank you all the participants. We have stopped the accepting your responses now, and the quiz is complete. So now your result of the quiz will be announced in the valedictory session. And now I welcome and hand over the screen to Dr. Seema Lal, who will present the valedictory session. It is over to you, Dr. Seema.
Thank you, Dr. Robin, and very good afternoon to one and all. Well, after successful accomplishment of 2 wonderful sessions, 4 very interesting, thought-provoking, and full of knowledge lectures, highly innovative and creative poster session, and an inquisitive quiz session, we have approached to the valedictory function of today's symposium. It's my high privilege to welcome our IQAC coordinator, Dr. Aditya Saxena sir, teacher in charge, Sir Professor Devanandan Kumar, our convener of the program, Ma'am Dr. Pratibha Kumari, all the respected teachers from our department and other departments, institutions, and all the dear participants. I, Dr. Seema Lal, Assistant Professor, Department of Chemistry, Deshbandhu College, on behalf of Department of Chemistry, take this opportunity to welcome you all to the valedictory session of International Symposium, Chemical Wisdom by Her. The symposium, Chemical Wisdom by Her, was successfully organized by the Department of Chemistry under the aegis of IQAC Deshbandhu College. It was designed to highlight the contribution of women scientists and promote the women empowerment in the field of sciences. Here, all of us are benefited by the words of wisdom of our distinguished, eminent speakers who have enlightened us about the synthesis of biologically important heterocycles, good manuscript writing skills, of nanomaterials by sol gel technology for various applications and processes. I am sure that today's symposium is a good to our younger girls to do excel in the scientific area. I am highly delighted and proud for this one-day international symposium in the form of registrations and participation. We have received over 750 registrations and 68 posters under experimental and theoretical sections in the area of health and medicine, green chemistry, women in sciences, nanotechnology, biofuels, environmental remediation, and many more. Our participants are undergraduates, postgraduates, research scholars, and faculty members from our college, other colleges of Delhi University, other universities, and academic institutions of India and abroad. Here, I would like to mention an announcement. I request all the participants to please fill the feedback form that will be posted in the chat box soon. So now, first and foremost, I would like to thank a very dynamic, cooperative, quick response giving, easily accessible, institution-oriented principal sir, Professor Rajiv Agrawal, who has always been a torchbearer with regards to academic progress of the college. Today, due to his prior engagement, sir has not joined the valedictory function, but he conveyed his best wishes to all the participants and the winners. Now I request a very calm, highly dedicated and sincere IQAC coordinator of Deshbandhu College, Dr. Aditya Saxena sir, to please address the gathering. It's over to you, sir.
Thank you so much, Seema. First of all, I would like to really congratulate the Department of Chemistry and I think Deshbandhu College that we have been able to successfully organize the International Symposium on Chemical Wisdom by her. And most notable, I think, feature of this symposium was that we focused on the achievements in the field of chemistry by the women scientists and researchers. So I think that was a very, very unique initiative, which I think, I mean, at least I don't remember that any department may have taken up to highlight the achievements of women scientists, especially. And also, I would like to, really extend my thanks to our chief guest for the day, Professor Balram Pani, our chief patron, who is also the chairperson of our governing body, Shri Aryan Vatsji, our very dynamic principal, the patron of this program, Professor Rajiv Agrawal. And I would really like to thank, on behalf of Deshbandhu College and the IQAC of Deshbandhu College, our distinguished speakers for the day, Professor Hriyan Kanwar Ila, Dr. Sumati Bhatia, Dr. Khushbu Kushwaha, and Professor Shivani Mishra. And I think on the whole, it was a wonderful program. And I feel that it is really nice that we have started this kind of a series of international symposia. And I hope that we continue with this, and more departments are encouraged to take up these kind of events. And especially I would like to congratulate the teacher in charge, Professor Devnandan Kumar sir, the convener of the program, Dr. Pratibha Kumari ma'am, the co-conveners, Dr. Archana Malhotra, Dr. Seema Lal, and Dr. Leena Agrawal, the organizing secretaries, Mr. Sanjay Kumar, Dr. Ashwini Kumar Singh, and Dr. Maku Morong Singh. And finally, also our Vice Principal sir, who's always there to guide us, Professor Kamal Kumar Gupta. So with these words, I would like to hand over back to Dr. Seema Lal. Thank you.
Thank you, sir, for your nice words. Thanks a lot. Now I request a highly versatile, very sincere head of the department, whose continuous guidance and untiring efforts and unconditional support has made this symposium a huge success. I request teacher in charge, sir, Professor Devnandan Kumar, to please share his views. Over to you, sir.
Thank you, Dr. Seema. Am I audible?
Yes, sir. Yes, sir.
Okay. With immense pleasure, I, Devnandan Kumar, teacher in charge, Department of Chemistry, welcome everyone to the valedictory function of one-day international symposium entitled Chemical Wisdom by Her. All the lectures were very informative, enlightening, and motivating. I congratulate the winner of poster presentation and quiz competition. I sincerely thank Professor Rajiv Agrawal, Principal, Professor Kamal Gupta, Vice Principal, Dr. Aditya Saxena, Coordinator, IQAC, for motivating us and timely cooperation at every level. My sincere thanks also goes to Dr. Archana, Dr. Seema Lal, Dr. Leena, Dr. Maku, Dr. Ashwani, Dr. Robin, Dr. Atul, Dr. Seema Gautam, Dr. Bharti, Dr. Gaurav for their hard work and cooperation. I also thank Dr. Pratibha for taking responsibility with dedication, hard work, and timely appropriate actions. My thanks also goes to all the faculty members of the department. Thank to all the participants for taking out time and participating and making the event successful. Thank you everyone who directly or indirectly helped in the successful completion of the event. Over to Seema. Thank you.
Thank you so much, sir. We always look forward to you for your encouragement and support. Now, I humbly request our senior most faculty member of the department, Dr. Vivek Saxena, sir, to please address the gathering and announce the winners of poster presentation. Vivek, sir, it's over to you.
Am I audible to everybody?
Yes, sir. Yes, sir.
Yes, sir.
Thank you. It was very good informative sessions I attended, and thankful to all organizing committees, especially Pratibha, who's taken so much pain and had put her hard work to make it success. And I'm sure that the participants must have been waiting for the results. So here I am with the results for the poster. Let me open the results provided by Dr. Pratibha. They are, first I will announce the list of judges who judged the presentation and had given so much pain to hear all the participants and come out with the results. The judges were for the experimental poster session, Mr. Bhavani Shankar, Dr. Parul Singh, Dr. Gajendra Singh, Dr. Manisha Sengar, Mr. Sanjay Kumar, Dr. Ashwini Singh, and Dr. Leena Agrawal. The results are: the first winner for the experimental section goes to, for this, I must tell that there were 40 registration in this section. In all, there were 68. And this section, there were 40 registration. And 37 presented their work, judged by these judges. The first winner is Nasimha Mamdi from the Department of Chemistry and Nanotechnology, School of Engineering and Science, Mexico. The title of their poster was Development of Stimuli Responsive Nanosystem for Environmental Remediation and Drug Delivery. Congratulations, Nasimha. The second prize goes to Mr. Vishal Singh from the Department of Chemistry, University of Delhi. The team was Vishal Singh and Professor Prabhati Vishwas. The poster was presented by Vishal Singh. Title: Stochastic Kinetics of Protein Misfolding and Aggregation. The third prize goes to Simon As. The team was Simon As, Neetu and Arif Ali Khan from School of Business, Basic and Applied Sciences, Guru Gobind Singh University, Dwarka, New Delhi. The title was synthesis of novel organophosphorus heterocyclic compounds and their derivatives. This was for the experimental poster presentation, and for the theoretical poster presentation, I have the judges list on my WhatsApp. Let me have that. It was just by our department faculty, Dr. Shilpi Khurana, Dr. Shilpi Patnagar, Dr. Moses Pinche, Dr. Ruby Mishra, Dr. Seema Lal, Dr. Seema Gautam, and Dr. Atul Sharma. In this part, there were total 66, and there were how many?
20.
Yes,
28.
28.
was there.
28, sir.
Good. It is not mentioned in the results you have given to me. Well, the first prize goes to Miss Megha. The team was Megha, Naitu Bhatnagar. Megha and Naitu Bhatnagar from the Department of Chemistry, Manipal University, Jaipur. The title for their poster was Self-Healing Polymers and Its Applications. The second prize goes to Kinjal Jain, the team. The Kinjal Jain, Vaibhav, Divyansh Singh, and Gitanjali from the Department of Chemistry, Pirodimal College, University of Delhi. Their title, the poster title is Stubble Burning Friends of Foe. The third prize goes to Palak Bhatt, presented by Palak Bhatt. The team is Palak Bhatt and Dr. Namita Gandhi from our department. Namita Gandhi is a private movement for our department, and it's from BSc program APS Industrial Chemistry, second year, Department of Chemistry, Deshmukh. The title of their poster was Overview of Biofuels as Sustainable Fuel Source. Thank you. Thank you, Pratibha, for giving me this chance to present the prize winners for the poster session. Thank you.
Thank you so much, sir, for announcing the results. And many congratulations to all the winners, Mr. Narsimha, Mr. Vishal Singh, Ms. Simon Az, Ms. Megha, Ms. Kinjal Jain, and Ms. Palak Bhatt. Once again, I request all
Excuse
the
me, ma'am.
participants.
Excuse me,
Yes.
ma'am. If that is Palak with Namita ma'am, then I think the surname is not Palak Bhatt. Please cross-check this.
She is Palak Bhatt.
Actually, two Palaks are there. One is Palak Bhatt, and another Palak is with Namita ma'am.
Yes, one is Palak Bhatt and another is Palak Pal.
Okay. Okay, then it's okay.
Okay. So participants are requested to please fill the feedback form posted in the chat box. And now I would like to invite a very enthusiastic faculty member of the department, Dr. Bhavani Shankar, to please announce the winners of quiz. Bhavani, sir.
Thank you very much, Dr. Seema Lal, for providing me this opportunity. And hope everybody is excited to hear the result of the quiz competition. But before that, I would like to share with you that a total of 147 candidates took part in this competition. And here we have elected 3 candidates as winner of this competition. And I would like to thank you all for your active participation in this quiz competition. Now, hold your breath to listen the name of the candidate who has secured the third position. And the name of this candidate is Rakshanda Singhal, Department of Chemistry. She is a PhD student. And the second prize goes to Prateek. Prateek is a BSc Chemistry Honors student at Kirodimal College. And first prize, can you guess who will be the first winner of this quiz? Okay, I'm going to tell you the name. He is Ramlal from Indian Agriculture Research Institute. So now congratulations to all and best of luck for other candidates who have not secured any position. Thank you very much. And now it's over to you, Dr. Seema.
Thank you, Bhavani sir, for announcing the result. And many congratulations to all the winners of quiz session, Mr. Ramlal, Mr. Prateek, and Ms. Rakshanda Singhal. We will mail you the certificate of appreciation soon. Now, it's a high time to invite the person behind this wonderful event who has implemented this concept of chemical wisdom by her in the form of an one-day international symposium. I request to our convener of the program, Dr. Pratibha Kumari, who herself is a very bright academician, an active researcher, and inspiration to many of us, to please come and pay a formal vote of thanks. Ma'am, over to you.
Thank you so much, Dr. Seema. Very good afternoon to all. A woman is a circle. Within her is the power to create, nurture, and transform the society. This was the main theme of this symposium, and this has been a great success because of the sincere efforts and huge participation of you all. In today's symposium, we had discussion on heterocyclic molecules, polymeric nanomaterials, soil cell technology, which have relevance in the field of medicine, agriculture, industry, and thereby impinging every aspect of human and creating a better world. We also had a brainstorming session how to write your result outcome to the scientific word in the form of a manuscript. I hope there is huge word of chemical wisdom as a takeaway from this symposium, and this is the success of this event. Now, I would like to congratulate all the winners of poster and quiz session and wish them many more success in their life. The e-certificate of posters and quiz winners, e-certificate of poster presentation, and all other certificates. All certificates will be emailed to all the registered participants subject to filling the feedback form. So it's very important to fill the feedback form. The link has been shared in the chat box, so please fill the feedback form. And you need not to worry about the certificates. We will email all the certificates to you because we have your email ID also. Now, on the behalf of Department of Chemistry, Deshbandhu College, I offer my formal vote of thanks for this symposium. I'm very thankful for our chief guest, Professor Balram Pani sir, Dean of Colleges, University of Delhi, Shri R.N. Vath sir, the chairman, governing body of Deshbandhu College, and our guest, Dr. Praveen Dhameja, advisor, Skill Council for Green Jobs, Government of India, for taking out time from their busy schedule and enlightening us with their thought-provoking views. I extend my gratitude to our distinguished speakers, Professor Echila, Dr. Khushbu Kushwaha, Dr. Shivani Mishra, and Dr. Sumati Bhatia for sharing their research expertise with us. We truly gained an experience that will last with us. Now, words may fall short to describe an charismatic, inspiring, and innovative principal, Professor Rajiv Agrawal sir. His guidance and generous support have made us to move ahead confidently. Her leadership has been the lighthouse in paving the way for successful implementation of this event at every stage. I extend my deep gratitude to sir for your unprecedented support and guidance. Thank you so much, sir, for being such a great pillar of support. My sincere thanks to Vice Principal, sir, Professor Kamal Kumar Gupta, and IQAC coordinator, Dr. Aditya Saxena. They have been so helpful in uplifting our spirit as ever. Our teacher in charge, Professor Devnandan Kumar sir, who played an instrumental role in stirring the thought for this webinar, which is exclusively devoted to acknowledge role of women and their significant contribution in the scientific arena. He has always been appreciative of hard work and toil of a woman. His suggestions have been a key motivating factor in organizing this event and bring together the warriors of chemistry. Thank you so much, sir. Now, many thanks to my ever enthusiastic co-conveners, Dr. Archana Malhotra, Dr. Seema Lal, and Dr. Leena Agarwal, whose tireless efforts have been the driving force to bring out the best in this international symposium. Their proactive approach at every stage, starting from the planning to the execution, have been beyond words. I am honored to have such marvelous and wonder women with us. My sincere thanks to the organizing secretaries, Mr. Sanjay Kumar, Dr. Ashwini Kumar Singh, and Dr. Maku for keeping the team focused with their candid opinion and then cooperating in every endeavor. My special thanks to the senior-most teacher of our department, Dr. Vivek Saxena sir, for his valuable guidance and suggestion for the improvement and successful execution of the event. Particularly, the poster presentation event was performed under his guidance. I am very thankful to Dr. Seema Gautam, Dr. Atul, Dr. Robin, Dr. Gaurav, and Dr. Bharti for their unparalleled dedication and passionate execution of every assigned task. My heartfelt thanks to Dr. Namita Gandhi, Professor Susila Singhal, Dr. Iswar Dutt Vats, Dr. Aparna Shekhar for chairing the sessions. And many thanks to Professor Ruby Mishra, Dr. Shilpi Khurana, Dr. Bhavani Shankar, Dr. Shilpi Bhatnagar, Dr. Parul Singh, and Dr. Gajendra Singh from Chemistry Department, and Dr. Manisha Sengar and Dr. Moses from Zoology Department for judging the poster session. I'm very grateful to Professor Mahesh Chandra, Dr. Umesh Kumar, Dr. Deepti Gupta, and Dr. Vishali Arora for wholeheartedly cooperating in organizing the symposium. Dr. Monica Bazaz has been a great support for handling the technical part of today's event, and even Leena handled it so well. So many thanks to Dr. Monica and Dr. Leena for handling all the technical parts. Last but not the least, my heartfelt gratitude to the young scientists and each participant for their overwhelming response. Their eagerness to learn more has truly made the occasion eventful. I hope our young scientists will appreciate the discourse of this informative session and incorporate the learning in their research activity. Now, I will conclude this symposium with the words of Michelle Obama that there is no limit to what we as women can accomplish. Thank you so much. Stay safe and healthy. Over to Dr. Seema.
Thank you so much, Pratibha ma'am, for your nice gesture and appreciable words. Thanks a lot. Once again, I request all the participants to please fill the feedback form posted in the chat box. Overall, it was extremely overwhelming and delightful experience. We have learned a lot from this worthful one-day program. With lots of best wishes, now we conclude this online symposium. Once again, thanks to all the speakers, faculty members, colleagues, students, and participants. Hope to see you soon in our upcoming international conference, tentatively to be held in the month of September 2022. Till then, stay safe, stay happy, and stay healthy. Thanks to all. Thanks a lot for your precious time and patience. Thank you. Namaskar.
Seema ma'am, you all are requested to switch on their camera for the picture.
Yes, please.
I am giving the permissions to all. All the participants are requested to switch on their camera for the picture.
Lena, your video is not on. Yes.
So let me end the meeting now.